Okay, hello everyone. So thank you very much for coming along. So my name is Cormac English, and this is Listening Like a Human. So just to get kicked off, a very brief introduction to me. I'm currently a DReal PhD researcher inside UCD at the moment. My focus at the moment is accented speech and automatic speech recognition systems. I wasn't always a computer scientist. Actually, I transferred over from law. So I did my undergraduate in UCD a couple of years ago, and then did the Masters of Science Conversion in UCD as well, because I'm very unimaginative. So I suppose that's get you set up. On top of that, an even quicker introduction to what this talk is going to be about. So very briefly, I'm just going to say what we're doing. So what is ASR? What are we trying to achieve? How we're doing it. So a very quick rundown on roughly where we are at the moment in terms of state of the art and why it doesn't always work. So that's kind of the key takeaway from this talk. So to get going, here's an incredibly brief history of ASR. So it's actually a very old field. It's been around since the 1950s. And just to explain what you're seeing on the right-hand side of the screen here, you'll see basically what you're looking at are what's known as spectrograms. So these are basically graphing power levels at different frequencies. So we use them a lot because they're a great way to capture a complete view of human speech. Now, underneath these, you'll see little characters, and they are referring to phonemes in English. For this set anyway. So basically a phoneme is a contrastive unit within a given language. So basically if you imagine dog and Doug, the O and the U, you have two different types of phonemes there, right? So it's important that these things contrast with each other. Now people don't always produce like a perfect representation of a phoneme. We're going to just produce what's known as a phone, a given sound, and then we kind of match it up to the closest one. But you can see there, just to be aware that it's important that these contrast. You'll also see that a lot of these look pretty similar, which is a problem we'll come back to later. But basically speaking, we have been moving from like identifying back in the 50s very simple sequences, like maybe matching the closest spectrogram to, or these clusters are known as formants, matching formants to like the word 1, 2. I think the first one was a machine called Audrey that could do 0 through 9 and plus and minus. So very simple mathematical thing. As time went on, the vocabulary started getting bigger. You 16 to 30 words through the 60s. By the 90s, you had very big vocabulary, so big databases of kind of idealized representations of words that we could try to match to what's coming in. Very stilted, easy to break, didn't account much for kind of I suppose the little minutiae of human articulation, and certainly didn't account for like inter-word interaction, that kind of thing. Today, I'm sure any of you in the tech sector are probably not going to be surprised. It's deep learning all the way. So we have very large deep learning networks at the moment. So, trained hundreds of GPUs, millions of sound utterances. It takes weeks to train, very large, huge data sets, very capable relative to their predecessors in terms of correctly identifying sounds. So just to give you a very brief rundown, so this is a picture taken from the WAV2Vec 2.0 paper, so that came out about a year ago. So WAV2Vec 2.0 is out of Facebook. It's quite a novel architecture insofar as the main training stage is focused on just trying to identify the sound units within a language, and then later on learning to map them back to characters and things. So typically speaking, there's usually a couple of layers in terms of whom we're trying to understand speech. So there's the audio layer, what does this audio sequence, however it's represented as an image, as a vector, what does that map to? And then a language layer where we'll try to impute language context to what we're hearing. Like if we go 3, 2, 1, hero, we might say, well, it's much more likely that we heard 0, that kind of thing. Now that causes problems on its own, but we have been getting more and more complicated. So this model is enormous, and it's also end to end. So that was a big thing. Stop treating it as kind of separate tasks and just give the data set over to a correctly designed model and hope that it's able to drag out the various patterns therein. And it does make it much more robust. It's much better at handling like the little slurs or improper articulations that humans make all the time. So seems great, wonderful stuff. We've got great metrics coming out. Things are 94% correct, that kind of thing. But it doesn't work a lot of the time, as I'm sure most of you will have noticed. So I've given a couple of very glib examples on the left here, but very simple things like single individual words just not being picked up no matter how much you talk to it. And that's actually something we'll come back to as well, this idea of responsiveness. Things claiming, as I said, 94% correctness, but then when they go into a production environment on an accented data set or something, everything falls apart, and suddenly you're running 80% correctness, 1 in every 5 words, so to speak, not being heard correctly, and so forth. So what's the problem? We don't know. No, I'm joking. We do know, but the problem is that knowing doesn't necessarily give us a very easy path to actually understanding or to resolving this issue. So at a very basic level, we are working with an enormously diverse set of data. So it's the unique sound production values of every human on Earth, because these systems are always generally interacting on a one-to-one basis. They're not talking to South Tipperary accent, they're talking to me. They're not talking to Glaswegian accent, they're talking to a person in Glasgow. So we end up with just an enormous amount of deviation within a given language, right? So we have accents. Within that, we have different types of accents. We have regional variations. We have L2 variations, so people bringing over patterns of enunciation from their first language, if it's the second language they speak, or the third language, or so on. And the scale of this can't really be understated. There are 7,000 languages being spoken at the moment within that infinite variation accents. So what has tended to happen, and it's very obvious when interacting with most of these systems, what has tended to happen is that we've ended up with high resource languages, high resource accents. So these usually map pretty closely, I would say, to what you might expect in terms of societal predispositions. So English is a high resource language, shocking nobody. And within English, then things like San Francisco Bay accent, very high resource. A lot of American accents are very well recognized. And then as the groups you're dealing with get smaller, and I say small here, we could be talking millions of people. That's still a small group. The quality of the data provided to the model and the representative nature of that data is getting smaller and smaller and smaller. And suddenly it's experiencing patterns of articulation and sound production that it's never seen. And it can only approximate, right? This is all only about approximation. So just to click on then, you might think, well, okay, that's fine, but humans do this. Humans listen all the time and understand language all the time. There doesn't seem to be that much of a problem. And that's true, but that's because humans are really, really good at this, right? So humans, first and foremost, we do something called perceptual learning. That's not something any of our networks really do. So perceptual learning basically means that I can be talking to someone, I can be in Normandy and talking to someone with a heavy Northern French accent, and they will have patterns of sound production that I don't understand too well. It's a phenomena that it will only take a couple of interactions for me to take these exemplars and really quickly evolve my understanding internally, my representation of if they're saying dog or things like that. I'm going to very quickly adapt to accommodate them, and vice versa. And similarly, if I go to talk to someone else from the area who's a similar accent but not the exact same patterns of sound production, I can bring those things over. So that's one thing, and we'll talk a little bit about that in a minute. But on top of that, humans have simply immense correctional ability. We can draw context from audio, from language, from conversational context, from personal interaction context. We have so many ways to repair defective, so to speak, audio coming in. If someone doesn't finish a word, I can probably guess what word they're going to say, and we can just move on, and I will do that subconsciously. To put it, I've written it there a bit glibly, generalized intelligence. We are, as we understand, a general intelligence. I can come in from so many vectors in terms of solving the problem. I'm not limited to one tool set. So in terms of what's going forward, I'll actually jump onto the next slide just to show you an example. It's not as dire necessarily as I make it seem, because we are trying very interesting things. So this is one example I saw about a year ago, whereby I think it was Mandarin Chinese. They were attempting to use a particular architecture to strip out accent-specific data from a particular piece of sound production, and separate that from the deviations or not the deviations, the patterns in the sound that were related to the underlying language. So try to take the word away from the accent, if you'd imagine it. Now, I'll be frank, and you can kind of see looking at this, it didn't really work. It kind of mangles it. And to be honest with you, it's probably a little linguistically suspect to be trying to disentangle accent and language, because they don't really come apart that cleanly. But we are trying novel things. So what's the timeline? we're not really sure. Perhaps we'll start moving towards few-shot models that are very interactive. So we'll have these models where you talk to them, you correct them, they develop some sort of a data unit for you that corrects for your speech. So maybe a layer on top of the network that corrects for you. Most likely, we'll probably just keep getting bigger and bigger data sets and more advanced model architectures, and they'll get a bit better. But it's still very much an open question, and it remains to be seen how much can be resolved just by throwing bigger data at it. You can ignore the magic. I left it there because PowerPoint put a unicorn beside it. So that concludes. Thank you very much, and thank you to the organizers of this event. I've made sure to thank them there so I can't forget.
Thanks very much.
No problem.
Yeah, no, that was a really great talk. That is a lot more about speech recognition than I ever knew. It's very interesting.
That was actually one of the challenges of this, was thinking, well, how much are people going to know coming into this? Because you start hearing things over and over again. You go, well, everyone must have heard of this, but it's not necessarily true.
Yeah, no, it's very true. So actually, you mentioned like that we have this ability to repair the audio. Is that something we could eventually approximate in our models, or is it too far?
Look, it's absolutely something we want to do, and there is this old saying that airplanes don't flap their wings. It's not necessarily the case that we have to copy what humans do in order to complete the same task. But at the moment, like, one of the biggest developments in recent years was this idea of transformer architecture that has an attention mechanism that basically means that inside, as it's weighing up things, it can take context from around it. So it can take context from the surrounding audio rather than just being bombarded with the context from the whole utterance. Now, that was huge, and it has made things a lot better. So there's nothing to say that we won't be able to incorporate more and better versions of that. Maybe in 10, 20 years' time, with the computational power we have available, we'll have very advanced AIs that are capable of kind of fixing themselves on the fly, taking information from the surrounding conversation, imputing that. There's nothing necessarily preventing us, except at the moment, I suppose, limits of computation. But at this, but at the same point in time, we're also a little bit constrained in terms of what we know about how humans perform these processes. Like, we do have fairly big old brains, and sometimes we can kind of get blown away by how great our models are, how fantastic they're performing. But at the same time, they're very limited, So it's all up in the air. I know this sounds a little bit disappointing. I'm sure people are hoping for me to swing in with an answer, but I was actually talking to a colleague during the week, and he looked up at me and he said, "Cormac, I've been doing this for 5 years. This might actually be impossible." So that's one side of things, but I think it is interesting to think about anyway.
Yeah, very much so. I mean, we do still need people to figure out if it is impossible. That's still very important.
That's absolutely, anyone doing a PhD, it's fine if you fail. That's a valid data point.
I'm glad we pivoted into motivational speaking now. I guess tangentially, you mentioned specifically about like in Mandarin stripping out the accent. Is there anything else that's kind of on the horizon of things that are very popular that we're trying now that could be achievable soon?
In terms of things on the horizon, so that was one random one. Another one I've seen is this idea of a few-shot model. So some sort of model that takes and adapts very quickly to novel exemplars or examples, basically. Cut the jargon. That they receive in a given piece of speech. So maybe it's something we'll see going through. A lot of people I've spoken to in the field are a little bit hesitant about this, because back in the day, in the 90s, you used to have to actually train up these models on your speech. So now, that was because they were terrible. But to a lot of people, that kind of harks back to that. So there wasn't, I've brought this up in a couple of conferences. There isn't an enormous appetite to have these models go back to having to talking to you. But at the same time, this is, I mentioned there, this kind of golden rule. If someone is saying Doug to me, and I haven't spoken to them before, there's no way to know what they're actually saying. Are they saying dog? Are they saying Doug? I can put in like language context, which is a big thing that we've been doing. So language context has been huge, and end-to-end models have made that language context much more robust. But at the same time, what you don't know, you can't predict. So you might need that interactivity. I'm not sure.
Okay. Well, that was very insightful. Thank you so much.
No problem at all.
Yeah. Thank you again.